This is the video podcast for Chapter 18 of Field Methods in Hydrology, and the topic is evapotranspiration. Now, you may remember from the water balance equations for typical watershed, where you're going to have precipitation, evapotranspiration, other fluxes, that evapotranspiration is the biggest outflux. And so it's very important for us to, of course, be able to measure it in a Field Methods in Hydrology course. So in this presentation, we're going to review the water balance equations because it's been a while, and I know that you really want to refresh yourself on them at this point. We're going to look at direct measurement methods for evaporation and transpiration. We're going to look at how to do evapotranspiration, and then we're going to look at energy balance methods. Okay, so let's begin with the two water balance equations. Let me remind you of the plot scale water balance. So this is where you have a very small piece of ground. Imagine 1 meter by 1 meter square as shown in this little schematic. And imagine just a 1 millimeter thin slice of soil with the air above it. For this interface, we have the precipitation that comes down on it. Being that this is bare soil, there's going to be evaporation leaving that surface. There could be water that runs on the surface and runs off the surface. And there can be infiltration to deeper levels below this 1 millimeter of soil layer. In addition, the soil and the air may contain soil moisture. That total volume isn't what's important, but the change in that volume. So I've got that symbolized here as plus or minus delta SM. Okay, delta just being change in that soil moisture or air moisture. So remember, this is the basic water balance for a bare surface. Now, when we scale this up to a watershed, the surface isn't bare anymore, and we tend to replace the process of infiltration with one for groundwater recharge. So the way this looks, here's a little watershed. It's got its little subcatchments for each of the tributaries. This doesn't look that different from, watersheds that we may go on field trips and play at. If you've been to the Schubert watershed, for example, it looks kind of like that, right? Okay, so we have then a three-dimensionality here where you can see the weathered mantle, which is like the soil horizon. In this case, as shown, it's not a very well-developed soil, but that's what's there. We have a bedrock layer below that, which might have some fractures that allow water to go in deeper. And then we have an outlet at the exit of the watershed. So when we look at the water balance equation, precipitation is the primary driver. We've covered how to do that for both snow and for rainfall, right? We've got our stream flow Q. We know how to measure that with a variety of methods now. We've talked about groundwater. We've talked about its flux using Darcy's equation. We've talked about doing pumping tests, things like that could be used for estimating what kind of groundwater fluxes you might have. We haven't yet talked about soil moisture and changes to that. This is plus or minus the change in soil moisture and depression storage. Depression storage we have talked about because you can just put a pressure transducer into your depression and see gains or losses that way. So the main thing we really haven't addressed here is evapotranspiration and soil moisture. Today we're going to cover evapotranspiration, and then later we'll be covering soil moisture. So the main thing here is you have a surface. It's going to be composed of a mixture of bare soils, grasses, shrubs, trees. It could be trees in different states of dormancy or activity. So trying to decide how you're going to integrate across all of that flux is an important issue to figure out for field methods. So let's begin with the basics and just refresh some concepts. If you've taken my HYD 143 class, you've already seen these concepts. This presentation is really going to be focusing on a variety of field methods compared to the other one. And we're not going to cover the Penman-Monteith equation, much to your relief, I'm sure. But anyway, we're just going to hit some basic concepts and move into methods along the way. So evaporation itself, a process by which the phase of water is changed from a liquid to a gas. Wherever we have water present, it could be on the surface, it could be in a plant or on a plant surface. It could be inside the soil but in contact with air. then there is a possibility of having this take place. So imagine here, like in this schematic, you've got a puddle on a road, and if we look in close at the puddle has, of course, the surface underneath it, the ground, and the puddle is receiving moisture. Not moisture, it's receiving heat from the ground, and there may also be wind blowing across it, and there could be heat from the sun. These are some of the factors that you'll see when we get into various equations that are going to be affecting the evaporation from the puddle. If we zoom in very closely on the surface where the blue line in this lowermost diagram is the water surface, then the molecules in the water have the ability of moving out of the water and into the air. And that escape process is essentially evaporation. When the ground heats up, it may allow these particles to move faster, and so then you can get more particles escaping. It's also important to understand that when water is transferred through the process of evaporation, energy is carried with it. And that's going to allow us to estimate evaporation using energy equation methods later on in this video podcast. 50 to 70% of water that falls is evaporated back into the air, right? So that's why this is really important. And of course, it's very hard to quantify with high degree of accuracy and precision. Well, the first technology for measuring evaporation is called a evaporation pan, which gives us pan evaporation. Here in the United States, we have the U.S. Weather Bureau Class A pan. It's 4 feet in diameter, has 10 inches of water depth, and you put it 6 inches above the ground. You can see in this photo there's a wooden pallet that is what keeps the pan off the ground, and it's, this is 4 feet across, so you can get that for scale. Now, when you look at this photo, there's a lot of things that are going on here. You can, of course, see a wind speed sensor here. You can see a rusty old box that has a data logger in it, a very new white cylinder. This has what you need for a pressure transducer. And then inside here, you can also see a weird gizmo that you can't really make out, but essentially what this is a very specialized kind of ruler for measuring the water depth manually. So instead of just taking a stick and putting it in the water and trying to read off of that, this has a very special point. It's actually like I'm turning my finger wrong. It's like a J. I'm not even doing that very well. It's like a hook. Actually, there you go. There's a hook. And it goes into the water, and then you measure to the tip of the hook. So this is something, again, like everything else, when you see it in the field, it'll make perfect sense. But it just allows for very precise water level measurement and the change in water level. So if you want to know evaporation, it's not just the amount that evaporates in the pan. Because if you look at this pan, you can see that the pan is exposed on the sides and the bottom. So that means it's going to be effectively heated from all directions. Whereas if you had like a lake, it's only going to be heated from the top, or of course the very bottom of the lake potentially, but not in close proximity to the surface where evaporation will take place. So conceptually, how does this technology work? Well, you have a water level here, say 10 inches of water depth, and you let some time pass, the air's dry, and the system evaporates. Then you come back, you measure how much water is there again, and the change in water over that time is your pan evaporation. Imagine a case where there's no precipitation, and you begin with a water surface elevation of 3 centimeters, and it goes down to 2. Then 3 minus 2 is 1, so you have 1 centimeter of change. Okay, it would be as simple as that. Now, it's a little bit more complicated because from the first time you measure to the second time you measure, there might also be precipitation. And that means you have to independently measure the precipitation because let's say your water level goes from 3 centimeters height to 6 centimeters height. You can't just assume that you've had 3 centimeters of precipitation because evaporation is taking place at the same time. So if we can independently measure the precipitation and know that it's 5 centimeters of rain, you start with that 5 centimeters of rain, and then you add to it the difference between the initial and after. And what you can see is we've had 3 centimeters of rise for 5 centimeters of rain. And that means that we're missing 2 centimeters here that aren't being accounted for. And so that's the evaporation, because it should have gone from 3 to 8 if it was just rain, but it only went from 3 to 6. And so the difference between 6 and 8 is 2. That's 2 centimeters of rain. I'm sorry, 2 centimeters of evaporation on the pan. Okay, so now as I was saying before, though, the pan evaporation is going to be more effective than just bare water evaporation, so we have to multiply it by a pan coefficient. It's a little unfortunate because CP is also the term used for heat capacity, so don't mistake in that, because we'll see it later on. We'll see the heat capacity. Here, this is the coefficient C for the pan P. And the pan coefficient ranges from 0.6 to 1. It varies by region, and you're basically downscaling the evaporation in the pan to get to an actual evaporation. Another thing that's important to note is that we have bare water here. And because it's bare water, that means you have an unlimited availability of water, so it's evaporating at the optimal rate based on the availability of energy to do work. But you could imagine there might be other circumstances in which, even with a lot of energy for evaporation, the water might not be so accessible, either because it's being held back by soils or plants or something else. And here's a map of the United States. A little bit tricky to see the outline of the U.S., but it's there. And it shows the mean annual pan evaporation in inches, ranging from 30 to the far northeast to over 100 in the southwest. And this just gives you a feel for that pattern. There's another technology for getting at evaporation or evapotranspiration that is a very simple device. It's underutilized, and so I like to mention it because it is very useful. It's called an atmometer. It's actually the inverse of a soil moisture probe that we're going to look at later called a tensiometer. It's the inverse of that. And in some ways, it's a little bit inverse of a rain gauge, because whereas like a rain gauge or a tensiometer, you're accumulating water, in this device, you're giving up water. So here we have a cylindrical reservoir, not unlike the one you'd have in a rain gauge, except it's already full, or it has a lot of water in it. Then there's a tube in the middle that goes to a ceramic disc, and a ceramic disc, if you think of like a kitchen tile or something like that, it's highly porous. It's a very good medium, so that when it has a lot of air area inside of it, so water that's on that porous cup is going to be easily evaporated away off that surface. And as it's evaporated away, water rises up through this tube and replaces it. So we have that ability to keep evaporating. Now, you wouldn't want debris falling onto the ceramic cup and contaminating it or blocking the pores, so you cover it tightly with a suitable cloth that's typically a canvas or Gore-Tex material. And it's also possible to take that baseline rate of flux and correspond it, or correlate it to values for different crops or other kinds of surfaces to be able to get a adjusted flux, to calibrate it basically for any crop or surface you want relative to the observed amount. So the main advantage of an atmometer, I should also say one other thing. If you look on the left, you could see that there's a tube on the sidewall, and then that is a graduated tube. So you could come out once a day and just read the value, and it will go down through time. And then at some point you have to go in and add more water. Now, you could also replace this manual measurement with a pressure transducer automated approach by just putting a pressure transducer into the reservoir and recording the water level drop through time that way. So the main advantage of an atmometer is it's very inexpensive, it's easy to use, it can be used to represent both evaporation and evapotranspiration, usually thought of as evapotranspiration though, because it's not, well, it's not like an open water evaporation, but it could be equivalent to a soil kind of evaporation, or that through a plant, as we'll see when we cover transpiration shortly. The biggest negative about it is, of course, you have to go out frequently and refill it, depending on the rate of evaporation that you get. And here's a real live example of one of these. It's made by the Colorado State University Cooperative Extension Group. It's called the ET gauge. And you can see the graduated measurement on the side. You can see the ceramic cup is the white, and it's covered with this green canvas cloth on the top. And it's all held together. And in this case, it's mounted to a post over turf grass. And so you can see it's not like it's in the canopy. It's not at canopy level, but it can be used both in the open and at canopy level, depending on what you're looking for. Also, they've done a lot of work to try to compare this to other methods, and of course other methods are not highly accurate or precise either, but it tends to be within 0 to 20% of other methods. So that just shows there's a lot of variability with evapotranspiration measurement anyway. Now let's move on to more approaches for how to measure evaporation. And to do this, we now have to understand more about the details of the process of how molecules leave the water and enter the air. So let's look at this simple experimental setup. Imagine we take a glass flask, and we put a rubber stopper and a thermometer into it. And we also have in the air a pressure gauge. If we were to begin with perfectly dry air and set it so that we have 0 pressure at that condition, then over time, maintaining the same temperature, eventually individual molecules will diffuse into the air, essentially. And as that happens, the amount of water vapor in the air goes up, and that also means that the pressure of the air goes up. So we would see a change on the gauge of an increasing pressure. If that were to continue, we would eventually reach a point where not only particles are coming up out of the water, but now we have so many particles in the air that they might also be bumping into the water and going back in the water. So we would eventually reach a point where we have almost equal amount coming out of the water as going in. It will never be exactly equal, but it'll still be close. And we could look at the pressure of the air at that point, and that is called the saturation vapor pressure for a given temperature. If we now put a heat source under that and heat it up more, then the capacity of the air to hold particles goes up because the particles become much more active. So many more are going to be bouncing around, and so many more will be going into the air, and we'll see a higher vapor pressure as a result. So I'm trying to introduce to you the definition of vapor pressure as literally the pressure that's there, like basically force per unit area imposed by things that are moving around in the air, and notably water vapor. And then from there it can saturate, and then from there, if we change the temperature, make it higher, we can have more and have a higher saturated vapor pressure. And in fact, there are well-produced relationships between temperature of the air, as shown on the x-axis here over a very wide range, and saturation vapor pressure. There are tables, plots, curves, there are equations that you can get for this, and in fact, you'll want to have that as a hydrologist. So we can now see that saturation vapor pressure versus temperature is a key factor. Now, why is this going to matter? Well, let's just look at it conceptually. If you have this very dry air, then you have a very high degree of what we could call potential or desire for this dry air to receive the water. On the other hand, when you're saturated, the air is like, nah, I've had my fill, I don't want any more. So it basically doesn't need to evaporate anymore. That's the essence of where we're going. So let me show you some methods now that relate to direct measurement of evaporation, taking advantage of these concepts. The first is a direct flux measurement method. And this is a fairly sophisticated approach, and it's going to require some technology. So on the left, we're going to have evaporation, E, and we can measure that directly, but I also would like to introduce, if you haven't seen this before, this script letter L, which is the latent heat of vaporization of water. This is the amount of heat that's being carried off with the water based on the water temperature as the water evaporates. So if you want to know the energy, then you want to know LE. If you only want to know the water flux, then it's just E. Now, why introduce this? Well, because it's the opposite. Because we're going to be measuring energy fluxes later, and we're going to need to go from energy back to water mass flux, and therefore we'll be dividing by L. But it's good to introduce that here. So LE equals L, okay, that's on both sides of the equation, times the density of air, and the density of air is a function of temperature, so I've given you a few values here, times kW. This is called the eddy transfer coefficient for water. Well, what does that mean? Well, this means that if you have water and you have air, then how effectively is the water moving into the air? Okay, eddy transfer. Transfer means the water is moving from one to the other. Eddy, an eddy, just like if you think about it in a river, an eddy is the swirling of the air that's taking place above the water surface, usually in response to wind. And so wind plays a role in carrying heat and moisture out of the water and into the air, and then through different levels of the air. Okay, then D here, this is D like from calculus, okay? And this is saying that the change in this little q versus change in Z. Now we have a problem because we've already used Q and little q for water discharge. You have to forget that now for the moment. This Q is representing the water vapor concentration, grams of water per grams of air. You'll also see the Greek symbol nu used sometimes, and sometimes you'll even see E used. We just have to be very flexible as hydrologists. Now, I don't really care what letter somebody uses, as long as they tell me what it means, then I know. And of course, in different contexts, you get used to different symbols of the same symbol being used for different contexts. So what this part is saying is the change in moisture as a function of change in elevation above the ground. Okay, let's think about this for a minute. What do we have here? We have evaporation changing in response to three main things. How dense is the air? How windy is the air so that it can refresh the air above where evaporation is taking place, bring in new dry air and get rid of the moisture that's there? And then exactly how much moisture is in the air? In many circumstances, the flow of water relates to gradients. We've seen this for surface water flowing down a slope. We've seen this for groundwater as it flows from areas of high head to areas of low head. Well, it's the same for evaporation. The stronger the gradient, that is the stronger the difference in moisture content of the air from the ground up to the air, then the faster the flux is going to be. And that's what this equation is saying. So what do we need to measure here? Okay, density of air, well, that you can just measure the temperature and calculate that. Eddy transfer coefficient, well, that's challenging. Let's just assume for here you can pull that out of a textbook, or it's going to relate to wind speed. So the main thing we really need to know is we need to be able to measure this change in moisture as a function of elevation. The amount of moisture in the air is called humidity. That's the absolute or actual humidity. We also have a variable called relative humidity. The relative humidity is the ratio of the actual humidity to the maximum level of humidity that the air can contain before water droplets begin to form, which is basically saying the saturated vapor pressure. So Q over Qsat equals relative humidity. So what this means is if we measure the relative humidity, then we can estimate, of course, Qsat from temperature. we can get the air density from temperature. We can get the latent heat of vaporization from the temperature of the water, and we can get the eddy transfer coefficient from the wind speed. So the key now is, how do you measure relative humidity? Relative humidity relies on a sensor technology that's very old, but has been updated with new digital methods. And we're going to see this method, I think we've seen it before, and we're going to see it again and again a couple of times. This is a device called the hygrometer. It's a sensor that's used for measuring the moisture content of the atmosphere, and it can be used to measure relative humidity. If you also measure the temperature side by side with relative humidity, then you can get absolute humidity, because the temperature goes to calculate Qsat, and then you can solve for Q. So this particular technology has to do with the fact that if you have something electrical, that the ability of electricity to flow changes depending on what's around it. Whether you have soil, air, water, some other kind of solid or hydrocarbons, it all affects the ability of electrons to flow. In this case, we have what's called a capacitive thin film polymer sensor. And I've taken this from the website of Visalia, which is a company that makes many different relative humidity sensors and has a lot of good information available. So what they do is they have electrodes which are sticking out, and there's an upper electrode and a lower electrode. Between them, there's a thin film polymer that's placed, and that thin film of polymer is going to be porous enough so that water can get into it. And you can imagine that if you start off whatever the humidity is that you start with, if it gets wetter or drier, then the electrical process between the electrodes is going to vary depending on that moisture content, because as I already said, the flow of electrons depends on the medium that's around it. And in fact, there's something called the dielectric property of what's around it, that dielectric constant or whatever. And we'll see this when we get to other soil technologies like time domain reflectometry. A lot of technologies are now depend on the effect of water in, around electrodes and their ability to affect the flow of electricity. Okay, so as the relative humidity changes around that in the polymer, then we get a change in the voltage, and so that's what's measured. And I'm sure there's some reference point, whether it's 0 or 100%, and so then it knows relative to that. So of course it's going to come with a factory calibration. There are methods for calibrating a sensor like this, but it's obviously not a very easy thing to do, because you need some independent way of controlling the humidity and measuring it. Some considerations for measuring relative humidity as part of an evaporation station. Okay, here's just a simple schematic of what a typical relative humidity sensor looks like from any company. They will typically have a full range from 0 to 100%, but the actual accuracy of that sensor is going to depend on the temperature, and it's going to typically be around 1 to 2%. It has a response time, so how long does it take for it to sense what is around it, and that takes about 20 seconds. So some things you need to think about first and most importantly is you've got to put the sensor in a shield that's going to keep moisture off of it and keep solar radiation off of it as well. So this is what one of those shields look like. So whenever you see that out at a weather station, you know that's where the relative humidity sensor is. Another thing is you need to, because we're measuring a gradient, you have to be pretty mindful about where you're putting this. And so, you have to put it in a place that's representative of the ambient conditions. Think about what are the wind patterns, what are the temperature patterns, what's the solar radiation. So basically just being mindful in the siting of it. And if you have very extreme conditions, either very high relative humidity or very low relative humidity, you're going to want to buy a specialized sensor just for those conditions. In the case of a very high humidity, you just run into the problem that you may have condensation and then evaporation and then condensation and evaporation, and that could over time allow salts to accumulate and degrade the ability of the sensor. So so let me just also summarize by saying with this direct flux measurement, obviously this is an equation. It's not that different than Darcy's law or other things. I mean, look, Q from Darcy's law equals some constant, which is permeability K times the gradient. Okay, so it's conceptually the same. We've seen this many times. So it's easy to get scared by the fact that you're seeing an equation, but so much flux is just like this. It's not even that different from a Manning's equation. I mean, again, it's a flux is proportional to the slope of the water surface times some indicator of velocity, which could be Manning's n, and you have your water depth. So I mean, there's basically all the same kinds of equations. They're flux equations. They're used extensively in physical science, and so you have to become comfortable with those. Okay, the next method is an empirical method. It basically is saying that what drives evaporation? Well, it's two things. One, dry air above water, and two, wind, because wind blows away the moisture that's above that water and brings fresh dry air. If wind brings fully saturated air over a spot, there's not going to be any more evaporation, right? So we have two variables here, Qsat minus Q at a given elevation Z, or altitude above the water surface. This Qsat minus Q term, this is the deficit, okay? So Qsat, that's the total water that the air can hold at that temperature, and Qz is what it's actually holding. The difference between what it can hold and what it's actually holding is called the deficit, or the moisture deficit, or the vapor pressure deficit. And that amount of moisture is what this could hold. The greater that number is, the stronger evaporation is going to be, because you have a larger concentration gradient. And then over here we have the effect of air temperature. I'm sorry, air temperature. What do I have? Of wind speed. Okay, and so the higher wind speed, like I said, you're bringing in more fresh air to receive that moisture. And this is predicated on the idea again that the air that you're bringing is fresh with less moisture. And in fact, this equation is most commonly used to determine evaporation over lakes in the arid western United States. And there was a famous report where this was done for Lake Mead, and it calibrated the values of A and B as shown below here. So, usually the height, again, is measured at either 2 meters or 10 meters above the surface, but that's a minor detail. So this equation is a lot simpler than the formal flux equation, but it's not that different. You're basically just saying, instead of seeing the full gradient, you're just saying, well, okay, I know the water surface on the in the lake is fully saturated, so I've got a complete gradient there from there to whatever I've got in the air. So I just have to measure what's in the air with a relative humidity sensor and temperature, and then you can go from there. Okay, I want to shift gears from evaporation to transpiration. So what is transpiration? Well, it's the process in which water is being moved through a plant and evaporated off of the leaves of the plant and therefore released the atmosphere. So transpiration it has basically three components. It has the process of water being taken up by the root system. It has the process of translocation, where the water is being carried through the tree stem up to the leaves. And then it has the actual transpiration that takes place on the leaves. So let's begin by looking at the soil surface. At the soil surface, there are root hairs, and the root hairs are going to be receiving water very similarly to everything else as a result of a concentration gradient, where lower concentration in the plant and higher concentration in the the ground, the soil around it. And in the next slide, I'll say that a little bit more technically, not in terms of concentration gradient, but in terms of a water potential gradient specifically. But anyway, the water then moves from the hair into the plant itself into the area called the xylem. Then it's going to move through the xylem, and it's going to make its way up through the stem, through the branches to the leaves. Now at the leaves, there are these open air spaces, these pores. And the pores are protected from the surrounding atmosphere by cells that are called stoma or stomatal guard cells. When these are open, then it allows fresh, dry air to get in there, and then evaporation of water out of the leaf can take place into the air. If these are closed, then it's going to be holding the water and reducing the amount of evaporation. The best way to think about this approach is a pull rather than a push. It's not the tree trying to push water out. What it is the atmosphere. It's the atmosphere sucking on the tree like a straw, sucking the water out, and that ultimately drives water to be sucked in from the soil into the tree. Here's a close-up of the stomatal guard cells in an open position and in a closed position. So you can see how there are these air pockets that are residing inside, and the plant has the ability to open and close to prevent that. So like if there's a drought, the tree is going to try as hard as it can to hold on to its water and make that smaller. Okay, so let's look at the actual process of how this takes place. And now why am I going to this level of detail? Because this is a field methods class. The reason is because this is going to be the field method. And the field method is going to relate to the fact that if you want to measure the flux of water, you have three choices. You could measure it in the leaves, say by trying to use super tiny sensors and measuring them in the air spaces or just outside the stomatal guard cells. But think about how difficult that would be, because the tree has many leaves and many places where evaporation is taking place. So it'd be pretty hard to measure it there. You could also measure it in the root system, but now you're talking about digging up soils and somehow, I don't know, measuring soil moisture through changes through time, but not due to evaporation in the soil, so that's not so easy. So really the easiest place to measure this is in the tree itself. So conceptually, I want to reiterate that what we have here is a gradient-driven system. The gradient relates to what we call the water potential. And this is something we're going to define in much greater detail when we look at soils as the matrix potential. But in effect, what's happening is the atmosphere is relatively dry and the soil is relatively wet. Between those two end members, you have the tree. So let's say, we can measure water vapor pressure as a pressure, right? So remember, you could have a pressure sensor and you could measure what is the pressure of water vapor. So if we measure the water vapor pressure, we could get a number of 0.1 megapascal. So Pascal is Newton per meter squared. Mega means millions of it. And we have this number negative, and I don't think that's very important now, but it's basically representing the direction. That is that the soil is holding on to the water with that pressure. Now, as the water goes into the tree is also holding on to it, but the pressure is going down. You can see it's becoming more negative. And meanwhile, the atmosphere is sitting here at negative 95 megapascals. So dramatically lower pressure, the partial pressure of the water vapor compared to what's in the soil. So we have a concentration gradient reflected in this pressure or this water potential, and the water is simply flowing from areas of high potential to low potential, which is what water often does. Not always, but most times if you have a direct pressure gradient and you have no other contravening force, then it's going to be flowing in that direction. So how do we take advantage of this to measure transpiration. Remember, transpiration is the total amount being evaporated through the leaves, but of course all of that water has to move through one simple convenient place, which is the sapwood. So if we have a tree, on the left, this solid line here is the edge of the tree and the air outside of it. On the right, the gray area is called the heartwood of the tree, and between those two is the sapwood where the xylem is located. Water is moving up through the tree, hence these up arrows. Now, imagine that we had no movement at all. Imagine this pen is not a thermometer, but is a heat source. If I were holding this pen in the air right now and the red was indicating heat, then you could imagine heat would be moving away from here, and especially if it was in water, it would be creating a cone of heat with the highest temperature right at the pen and decreasing temperatures moving away. And you could imagine that that would probably look like a bell curve or some sort of normal Gaussian distribution moving away from there. Okay? The process by which heat moves away from an individual source is a diffusion-based process, again, governed by the gradient, unless you have some sort of turbulent mixing or something else going on. So you have a nice bell curve that's around here. Now what if I take a bell curve and I apply a unidirectional gradient to it? Well, what's going to happen is that source of heat is going to primarily be moving in the direction that flow is going, but still some is going to move upslope too because diffusion is going to carry it that way. And if you go back to the Environmental Tracers video podcast, you'll see many examples of plumes. They're not necessarily heat plumes, but heat works the same as contamination and everything else, pretty much. So what happens here is we're going to take advantage of this. You've got the unidirectional flow taking place from the bottom moving up, and we're going to put into the tree a heating element. Don't worry, we're not going to hurt the tree, but we're going to put this heating element in there. And as we heat that up, it's trying to make a cone around it, okay, a bell curve. But because of the unidirectional flow, then more of that heat is going to be pushed up the tree and less of it is going to be moving down. Then 10 to 15 centimeters away from the tree, we're going to poke the tree again. This time we're going to put in a thermocouple. And you'll remember from the water quality presentation where we covered temperature, a thermocouple is the device that we use to measure temperature. So we put the thermocouple in, and we're looking to see how hot we are at the thermocouple compared to how hot we're applying heat to the tree at the heating element. Now, if the flow is very, very fast, then it's going to be pushing the heat away relatively fast. So the ability for the heat to move 10 to 15 centimeters against that current is going to be hard, but some will do it, and so we will see an increase of temperature. Now imagine if the flow is very, very slow. Well, if it's very slow, it's going to be easy for the heat to move against it, and we're going to get a very high temperature at the thermocouple. So there's an inverse relationship between temperature and sapwood water flux. The higher the flux of water up, then the lower the temperature at the thermocouple. So this is called sap flow measurement because a relationship is made between temperature and flux rate, and we can use that to say, well, if the water is moving up, it's a steady state mechanism. So however much is moving up is how much is evaporating at the leaves, and that's the transpiration measurement. Here's a plot showing some typical data from transpiration measurement by sap flow. On the x-axis is time from midnight one day to midnight the next day. At the top is the vapor pressure gradient, and this is shown for a sunny day with the dotted line and the rainy day with the solid line. So, of course, on a sunny day, you're going to have a vapor pressure difference even at nighttime. It's still, there's a lot of heat that's carried over. That means that there's going to be a vapor pressure difference. But when you get to the heat of the day around 10 a.m., the vapor pressure difference goes up. It's going to fluctuate but reach a peak and then eventually come down. And that vapor pressure difference is going to be a lot higher on a sunny day than a rainy day. So what happens with sap flow? Sap flow is going to be really small, almost zero in the nighttime. Then as the vapor pressure difference goes up, so too does sap flow, right? Because the atmosphere is literally pulling the water from the soil through the tree and out, and the sap flow therefore is related to that. Now it's not perfectly mimicking it, but you can see it is showing a relationship. Okay, let's move to now some more technologies for evapotranspiration. This is an evapotranspiration measurement primarily because it's used for ground surfaces that are typically vegetated, either with grasses or with crops, but it even could be for a bare soil as well. So we have this device called a lysimeter. What a lysimeter does is it weighs the ground, and as the weight goes up through time, it's gaining water, and as it goes down through time, it's losing water. Obviously, you have to account for precipitation, just as I showed for the pan evaporation, but I've suppressed that for now. So when we look at this schematic in the lower left, you see a giant scale, just like the kind of scale you stand on to find out how much you weigh, except instead of the weight changing because we all eat lots of candy bars or whatever, the weight's changing because the ground is eating water, drinking a lot of water. So you put the soil onto a scale, and you're usually going to try to offset a lot of the weight with a counterweight so that you can use a fairly precise scale. Remember that the accuracy of any sensor is proportional to the full scale. So if you have you have to weigh 10,000 pounds, then it's not going to be accurate to, a tiny change in evaporation. So instead of doing that, we offset a lot of the weight with a counterweight, and so therefore you could use something that only has to measure a much more sensitive range of weight. So we have evaporation equals the total mass of the system minus the mass of the soil at time 1. So that difference is the mass of water, assuming all that's here is, okay, you've got vegetation and whatever here too, but it's basically the water at time 1 minus the mass of water at time 2 divided by time, and that's your mass flux. So you simply, you know either an initial state or whatever initial period there is, and then you're seeing the gain or loss. How do you know how much water is stored? Well, you could. It depends on how you begin your lysimeter, but if you begin it with a known moisture content, or if you measure moisture content through time using a variety of technologies that we're going to cover with the soil moisture presentation, then you can get that. If you don't know the mass of the soil, you can just look at the changes through time and attribute that to the water component. And then the last thing is that you can convert this to a depth flux, like if you want to know, millimeters of evaporation per day instead of a kilograms per day, by taking the mass, dividing it by the density of water. So that's going to convert it from kilograms to cubic meters, and then divide that by the area of the pan, which is going to then leave you with, like millimeters of water per time t. And here are just some photos that illustrate, some moderately sized lysimeters. They come in a wide range of sizes. Here at UC Davis, we have 2 extremely large lysimeters, and we'll go down into those and check them out. Now we're going to shift gears from the direct and indirect methods of measuring evaporation and transpiration and evapotranspiration together, like the lysimeter, to the energy balance methods. So for the energy balance methods, we're basically going to take advantage of the fact that evaporation is not only a water flux, but it's also an energy flux. And the flux of energy begins with the energy from the sun. So we have solar radiation that's coming in, and that solar output that's coming to the Earth is 2 calories per square centimeter per minute. If we look at the distribution of that energy by its wavelength, and this is something you may have seen if you've taken a remote sensing class, you can see in the yellow that distribution, and you can see the range from ultraviolet to visible to infrared light. In the red is the amount of energy that we get, watts per meter squared per nanometer of wavelength that actually reaches the ground. So some of this gets lost in the atmosphere and such. And so you can see that some of this is suppressed because of different constituents in the atmosphere. So this energy that's hitting the ground is then available to drive evaporation. And that means we set up an energy balance equation. On the left is the net radiation. Now, what do we mean by net? Well, it's not just that energy is coming in, but the surface is also giving off long wave radiation. And it's not just what's coming from the sun, but it's also coming from the clouds. So I feel like this is something that I mentioned already. I can't remember why, but anyway, somehow net radiation came up, and it basically relates to the energy coming from the sun and from the clouds, offset by what's leaving the ground. I remember we covered this when we covered the lake water balance, and I showed a lake energy balance. I knew it was in there in the dim recesses somewhere. Okay, so we have net radiation, and then what's that balanced by? Well, we have losses in terms of sensible heat flux. Okay, that's the shortwave radiation that you feel as a change in temperature near the ground surface. We have the actual soil heat flux, so energy that's leaving the soil through the process of conduction. And then we have the evaporative heat flux. And here I'm using capital L, but this is the same as that cursive L that I showed earlier. And that's because the LE is the energy flux associated with evaporation. So let's look at the technologies that we need. We need a technology for measuring net radiation, for measuring sensible heat flux, and the subsurface heat flux. If you could solve for all of those, then you could simply calculate evaporation. Now, why would this be better than all the other technologies? Well, different circumstances are easier or harder. I mean, if you're over a forest, for example, you're not going to use a pan. You might try to use a direct flux measurement, but there's a lot of challenges. And usually, it's not enough to know one component, but we are interested in all of these components. So we'll show you more of the practical ways in a minute, but this is the overall energy balance that we begin with. So net radiation is measured with a net radiometer, which is about a $1,000 device. And you can see it has these two spheres. This is how you get the net, because one sensor is looking up and one sensor is looking down. The difference between those two is the net radiation. So the net radiation, sunlight, the skylight is what's coming from clouds or other things there. And then we're subtracting what's being radiated off the ground. When you're considering net radiometers, some things to think about are, what is the range of wavelengths that it's actually recording? Do you need to go high up into these infrared wavelengths or into the UV, or is it mostly giving you the visible wavelengths? So that's something to be aware of. What is the sensor doing? There's also the voltage sensitivity. So for, if your data logger can record, 5 millivolts, then how many microvolts per, different change in energy or radiative flux. The operational temperature range, so can it work in very hot conditions or very cold conditions? And then the response time, how long does it take for the sensor to register the change? Then there's the soil heat flux sensor. This is a plate that you see here in this photo. And what happens is you excavate into the ground, not particularly far, but like 4 to 8 centimeters depth, and you install this plate, pushing it into the sidewall. And the key here is you really want to have good contact with the soil. Then you could backfill that. And you're also going to put a temperature sensor halfway up between the surface and the plate. Ideally, you'd have multiple temperature sensors, but often not. What we're worried about here is, we're trying to measure how much heat is leaving the ground through the soil because it's the overall energy balance. And so the plate is going to be measuring a flux, but of the heat that's fluxing past that plate, some of that is going to be stored in the ground, and that can be recorded with the temperature or the temperature gradient in the ground. Here's some examples to illustrate this. The dashed line is the observed heat flux at a plate at 4.6 centimeters underground. And you can see it's fairly smoothed out. In the middle of the day, we're having a positive flux, and later in the day, that's a negative flux. So I'm assuming here that a positive flux is heat going into the ground because it's hot out during the day, and then at night we're giving off heat. Now that's what's being recorded at 4.6 centimeters depth, but when we apply the temperature correction, you can see significantly higher and more variable fluxes of heat at the surface. And so that's why it's important to do this correction. So the correction involves taking the soil heat flux at a depth Z, like 4.6 centimeters, and subtracting from it the heat that's stored there. And so we have a temperature gradient here, dt dt, right? So this is the change in temperature through time. And we've got dz here, so we're integrating through the depth. So how is temperature changing through time? And we integrate that over the depth. So you can imagine like an integral function here. And then we multiply that by Cp, and I warned you earlier, this Cp is the heat capacity of that soil, joules per cubic meter per degree Kelvin. So we have the heat capacity of the soil here. And so we subtract that from this. And so you can see we have the heat flux plate, we've got one or two temperature sensors, and then the heat capacity you can just get from, from a textbook or the internet or whatever. So it's a relatively simple thing to measure, but in terms of doing it well and accurately, like most things in the soil, it turns out to be fairly hard and problematic and discouraging. Well, isn't that true at all of hydrology? Okay, so now if we return to our energy balance, remember we had net radiation, sensible heat, ground flux, and evaporation. So the next one is our sensible heat flux. We've got another nice, lovely gradient function. And now sensible heat flux is called sensible because you can sense it. You can feel that. It's the change in temperature over a change in elevation above the ground. And again, we've got, just like we had with the evaporation equation, we've got the density of the air. We've got an eddy transfer coefficient now for heat instead of water. And we've got the heat capacity again. Okay, and so, basically you just need a temperature sensor. You put that at two elevations, a high elevation, low elevation above the ground. You're going to co-locate your humidity sensors there as well, but this allows you to get that sensible heat flux. So that takes us to a very common method called the Bowen Ratio. So if we begin with our energy balance equation, and now let's define a variable B as equal to the sensible heat flux over the evaporative heat flux. Then remember here I'm putting the two equations in these small boxes to show you. Density of air is in both equations, that goes away. If we assume that the wind is equally effective at moving heat as it is moisture, then those would go away. dz goes away. So all we're left with is the ratio of heat capacity to the latent heat of vaporization and the change in temperature and the change in moisture as a function of elevation. So that's summarized here, CP over L and dt over dq. So the way we can use the Bowen ratio is shown here, just some very simple algebra. If we apply B into this, then we get this equation here, that the net radiation equals the Bowen ratio plus 1 times LE plus the ground flux. So you can get rid of the ground flux if it's not that big. So all we have to do is, in order to estimate evaporation, if we assume a negligible heat flux, measure the net radiation and measure the Bowen ratio. That means measure temperatures at two elevations above the ground, and at the same elevations, measure the moisture flux. So again, we've got some equations. I know that can be a little bit daunting, but if you want to understand it from a field methods perspective, you just have to measure two things. Just go buy a net radiation sensor, Okay, I lied. 3 things. Net radiation sensor, a relative humidity sensor, and a temperature sensor. And good news, it really is 2 things because you can buy relative humidity sensors with temperature sensors. And you can see in this big station here, there are these 2 looking, white things here, look like phasers or something. But all this is a relative humidity and temperature sensor with shielding over it. And it's at 2 heights. And I would imagine that somewhere on here is a net radiometer, and you can get your evaporative flux. And this is just a final graph illustrating field data showing the fluxes of each term. So the evaporative flux is the squares. Let's see, squares. So really this very small number here. The sensible heat flux is the dots. The ground heat flux is shown as this thick solid line. And then let's see, what else do we got here? The sum of everything, it looks like, is shown as these diamonds. So overall, in this particular case, which I think happens to be in Israel, it's a case where there's a relatively high ground flux, but you can see, the sensible heat flux is about the same as the ground flux. So here, evaporation is relatively low in terms of watts per meter squared during the day here, okay? But then you can see at night we have, it stays low, right? Okay, so it looks like in this case, the ground flux is the largest flux that takes place with its fluctuations, with sensible heat flux being very large too. So you can see that the role of evaporation, evapotranspiration, is going to be very site dependent, but you can use an energy balance to get at it. So overall, what we've covered in this presentation are direct measurements to get at evaporation, like the flux equation. I should say, by looking at the gradient in moisture with height above the ground. We've looked at pan evaporation, atmometer. What else did we do? We had the lake evaporation with the empirical equation, right? Then you go to transpiration, and sap flow is the go-to for that. You can put evaporation and transpiration together either with an atmometer with the right cover or with a lysimeter. And then finally, you can use an energy balance approach to estimate evapotranspiration by putting relative humidity and temperature sensors above the canopy at set heights, and also looking at net radiation.